In this lecture, I'd like to take a look at some of the ways in which calculus is used in computer science. Calculus is, after all, a practical discipline and has many uses in a wide variety of different areas. The goal here is to be able to analyze the amount of work done by a computer algorithm. In this way, we can predict how long an algorithm will take as the problem size increases. When we talk about problem size, we talk about such things as if you are going to sort a list of items, how many items are in the list. For instance, if I want to sort a list with 100 items, that's going to be much faster than sorting a list with 1,000,000 items. Thus, when we talk about problem size, what we're talking about in this case is the number of elements in the list we're going to sort, because that has a direct impact on how long the algorithm will take to complete its work. So as an example I have here, imagine that you're a programmer for a certain company. Your boss comes to you one day and says, "We just bought out our rival and now we've got twice as much business." Every night the company has an information system that runs, and on average it takes 3.5 to 4 hours to complete the process. The boss wants to know how long it's going to take now that now that the company has bought out its rival and doubled the size of the problem. Will it take twice as long? It turns out that not all algorithms are equal. It may seem intuitively obvious to you that if you double the size of the problem, it's going to take twice as long, but it turns out that that's seldom the case. Sometimes it is, but very often it is not. Here's an example of two algorithms. In the blue on the bottom, we have a linear algorithm. If you double the amount of work needed to be done, it takes twice as long. However, the orange line is actually an n-squared algorithm, and as you double the size of the problem, it takes 4 times as long. Thus, if it took 4 times as long, if we go from 3 to 12 hours, it becomes too long and may be a problem for the company. Again, there's a wide variety of complexities that you will see with computer algorithms. These are examples of logarithmic, exponential algorithms and the growth rates. What we're after here is the rate of growth as the problem size gets large. So as an example of how to do algorithm analysis, I want to take a look at a fairly common and a not very efficient algorithm for sorting lists of numbers. This algorithm is called bubble sort. The way this works is you scan down the list looking at each pair of numbers and you swap them if they're out of place. So for instance, with the first pass, we have 17 and 12. We see that 12 is smaller than 17, so we swap the two and move down to the next set. We swap the 8 and the 17, the 3 and the 17, and finally the 17 and the 7. So we have made one pass through this list of numbers, but the list is not yet sorted. What has happened is the 17 has been moved into last position, which is where it will go. Notice the number of comparisons we have made. We have compared 4 pairs of elements, and there are 5 elements in the list, which is to say we just did n-1 comparisons. Now going through the list again, the 17 is where it belongs, so we don't ever have to look at it again. We have the 12 and 8, and we swap because 8 is smaller than 12. 12 and 3. 3 is smaller than 12, so we swap. 12 and 7, again 7 is smaller than 12, so we swap. So this time we have done 3 comparisons, or n-2. The 12 and 17 are now where they belong in the list, and we don't need to look at them again. So thus far we have done n-1 comparisons plus n-2 comparisons. We go again because our list is not yet sorted. We swap the 8 and the 3. Going down to the next pair, we swap the 8 and the 7. So now we have 3 elements that are where they belong. This time we've done n-3 comparisons. So we have done n minus 1 plus n minus 2 plus n minus 3 comparisons at this point. Then finally, the last pass, we check the 3 and the 7, but we don't swap them, but we did do the comparison. So if you count the number of comparisons needed to do the swaps, you will see that you have n minus 1 plus n minus 2 plus n minus 3 down to 1. Or written another way, 1 plus 3 plus 4 plus up to n minus 1. This is an identity. This is n times n minus 1 over 2. Thus, the function that describes the rate of growth at this algorithm is n squared. What that means then is if we double the size of the list, the number of comparisons we are going to make roughly quadruples. From 5 to 10, we go from 10 to 45 comparisons. This is the rate of growth. This is what tells us what happens as the input size grows large. Very often we need to compare two algorithms. Is algorithm A faster than algorithm B? When we say faster, what we mean is that the faster algorithm has a slower rate of growth. It runs more quickly. So given two algorithms A and B, the first, the function is f of n, and the second, g, is n squared. A is the faster algorithm because it takes less time. It grows at a slower rate. While there are several ways that you can rank functions according to rate of growth, perhaps the easiest and most intuitive is by using limits. So there's a small chart here. As you can see, the limit of the ratio f over g, these are the two functions. If the limit is the size of the problem goes to infinity, f over g, if it is 0, this means that the denominator, the one on the bottom, g, grows at a faster rate. If the limit resolves to a constant that's not 0, then they both grow at the same rate. However, if the limit as the problem size goes to infinity of f over g is infinity, this implies that f grows at a faster rate than g. Thus, there are times when we need to figure out which algorithm is faster, and we use limits to determine that. So here's an example of a fairly common problem. Algorithm number 1 is n times log of n, and algorithm number 2 is n to the 3/2, or n times the square root of n. So to figure out the ranking of these algorithms, we perform the limit as the ratio goes to infinity. So here we have n to the 3/2 over n log n. So we take the limit of these. First, we can eliminate an n. We can remove an n from the numerator and the denominator, leaving us with the square root of n over log n. Taking limits with logarithms is somewhat difficult. Therefore, we use L'Hopital's rule, and we can take the limit of the derivatives instead. So here we have the limit as n goes to infinity, the derivative of the square root of n over the derivative of log n. Taking these derivatives, then we have 1 over 2n to the 1/2 over 1 over n, and here's the big payoff with L'Hopital's rule, because the derivative of log n is 1 over n. Now we have substituted the natural log for log base 2 here. We can do this because all logs grow at the same rate. As an exercise, you might want to take the limit of log base 2 of n over log base 10 of n and see what you get. At any rate, once we have solved this, taken the derivative, the rest of it's fairly trivial. Here at the end you can see n grows at a faster rate than n to the 1/2. We have infinity. Therefore, the numerator grows at a faster rate than the denominator. N to the 3/2 grows at a faster rate than n log n. N log n is the faster algorithm. So by using some simple calculus, we can solve a problem that would otherwise be quite challenging and quite difficult. This makes it invaluable for analyzing algorithms in computer science. Logarithmic functions are very commonly seen in computer science. We have them a lot, and so this turns out to be a very useful tool.